This is example number 16 of chapter 13. So we are here working with the analysis of kinetics relating force and acceleration. So we have a skier that is going down this slope, and whoever designed the slope gave a shape of a parabola, and we have the function of the parabola, which is 1 over 200 x squared minus 200. And they want to know what will be the acceleration of the skier right at the end of the slope and the normal force between the skier and the ski slope. First of all, we do our free body diagrams, and then we have to decide which type of coordinates we will use to solve this problem. So we do our free body diagram of the skier, right, at A. So I'm going to consider the skier as a particle, which is at A, and what forces do we have at A? We have the weight and the normal force. We actually do not have any other force. And then we have our kinetic diagram. To do our kinetic diagram, we have to decide which kind of coordinates we have to use. Since it's a curvilinear motion and we are not giving r, so we are not deciding to use r and theta, we are going to use tangent and normal coordinates. So here is my tangent direction. So this curve goes like that, but the velocity is tangent, and this is normal direction. So that's what we are going to use. And as we see, we will have then our mass tangent acceleration and our mass normal acceleration. As you recall, this normal acceleration is velocity squared over radius of curvature, and as you recall, the tangent acceleration is the derivative of the velocity. So if we do our equations of motion, which is the same as force equals mass times acceleration as a vectorial function, we can do our forces in normal direction, in which case we will have normal minus weight equals mass velocity squared over radius of curvature. And if we do our tangent forces, here we don't have any force, so we have 0 equals mass times velocity dot. So here we see that at that point, rate of change of the velocity, which is the tangent acceleration, is equals to 0. So my tangent acceleration, which is the velocity dot, is equals to 0. So that's the first result that we find. Let me place it right here. So our tangent acceleration is 0. That doesn't mean that the acceleration is 0. We still have a normal acceleration. Remember that we have two components, the normal and the tangent. Then we have only one equation left, and we have actually two knowns because we have the normal. The weight is known, but then we have the velocity is known, but we have the radius of curvature is unknown. So we can find the radius of curvature because we have the shape of our skis jumped. So if you recall, if you don't recall, you can look it up. That will be in your formula sheet. The radius of curvature is 1, right? The derivative of y, the x, this 2 squared, and all that 3 over 2 divided by the second derivative. So here we have to find the first derivative. So this is a very simple equations to derive because it's just a polynomial, right? So the derivative of a constant is 0. The derivative of x squared is just 2. X will be 200, and at top will be 2x. So this is equals to x divided by. But we have to evaluate it where we want to find our system, and our system is at A, and as you see the system, the coordinate system, that equation is given for this coordinate system. So x is equals to 0. So we will evaluate that x equals to 0, therefore this is equals to 0. The second derivative will be equals derivative of that expression, which is 1 over 100. So finally, we can plug in those numbers over here, and we plug here, we will have 0. And then we have 1, 3/2, and then here we will have 100. At the end, this is 1 over 100, so we actually, from here we see, evaluating the expression, we have that rho is equals to 100. This is one result that we need, and then we will plug at that here. So having that number, we can find that our normal force is equals to weight, which is 150, plus mass, which is 150 divided by 32.2. You know that in customary units, you know that the weight is a primary unit, and you have to divide it by the gravity to find the mass, times the velocity is given, which is 65 here square, divided by 100, which is my radius of curvature. From here, I have already calculated this value. Let me see, 346.8 pounds. This is the second value that we get as a result. We still have to find the acceleration because, as I said, the acceleration is not necessarily equals to 0 because we found that the tangent acceleration is 0. You recall that acceleration is the two components, and this acceleration is equals to 0, right? But that one is not. So actually my acceleration is the normal acceleration, and the normal acceleration, velocity over radius of curvature. Well, it's actually this value right here, right? So, and the acceleration, I calculated this value right here, and the value is equals to 42.25 feet over second square. And that's the solution of the problem. So we were able to find the normal force right here and the acceleration at the end of the slope.